Okay. So the record bar started. At least let me check if. Okay. So let's come back to our power series. Yes, this is our power series, and I told you that the basic example, the basic result here is about the geometric series. This is when we will compute the sum. Now, first of all, we need to compute the radius of convergence. Now, the radius of convergence, it's a simple formula. If you have sum of an times xn, the radius of convergence can be computed in two ways. In most cases, in some of them, only one method. This modulo of n plus 1, or equals limit when n tends to infinity of 1 over root of order n of modulo of an. In most cases, these two limits are equal. It may happen that the second limit exists and the first one doesn't, but in our usual exercises, both can be applied. Okay, so in our case, it's simple to observe that the radius of convergence is 1. Finally, it will give you something like that. Which is 1. So what we know in this moment? We know that if modulo of x is strictly less than 1, our series is absolutely convergent. So on the interval, open interval minus 1, 1, our series is absolutely convergent. And now, in order to find the domain of convergence, remember that our second question was about the domain of convergence. Now we need to know what happens at minus 1 and at 1. So if x equals minus 1, we get a series. This series. Minus 1 at 2n, it's 1. So we get the series. How is this series? Is it convergent or divergent?
Convergent.
Obviously convergent, yes. So actually they are both convergent, yes, at minus 1 at 1. So the domain of convergence will be the closed interval minus 1, 1. Because at both ends of the interval, we obtain a convergent series of numbers. Okay. We can observe, but it's not important in our exercise, that at the ends of the interval at minus 1 and 1, the series is convergent, but not absolutely convergent. So you see, on the open interval here, we have absolutely convergence, while at the ends of the interval, the series is still convergent, but just convergent, not absolutely convergent. And of course, outside, it will be divergent. Okay, it's not a general result, but it happens in this example. And now let's compute the sum of the series. Here, I repeat, the basic result is to use, the basic idea is to use the geometric series. This is it. So somehow we must reduce our problem to compute the sum of a geometric series. And now the usual methods are with derivation or integration term by term. So think, what should we do to this series? So we shall denote by s of x the sum of this series. So our question is to compute this function to find a formula for just to compute the sum of the series. Finally. And how can we get the geometric series? Okay, of course, if we compute the derivative of s, which is this one, yes. Why do we compute the derivative? Simply because we observe that n will simplify. Our problem, it is this n here. Without this n, we would have a geometric series. So we compute the derivatives. Now we shall use a theoretical result which says that a power series can be derivating term by term. So the sign of derivation from here outside the series can be translated inside. Of course, -1 at n over n, it's a constant. So finally, what we need to differentiate is x at 2n, which is this one. And now the reason we did that is now we can simplify by n. So it gives us 2, which is a constant and goes outside, times -1 at n, x at 2n minus 1. And now, normally, we can compute the sum of this series. Here, it's good to write maybe few terms in the beginning to understand better the behavior. So when n equals 2, you get x at 3. So the series starts with x at 3. This is the first term. That's important in order to compute the sum. It doesn't change the convergence. I mean, the domain of is the same, but the fact that the series starts with x at 1 or x at 0 with x at 3 here, it's important for the sum. Okay, plus, then n equals 3, it's minus x at 5. Then plus x at, if you put here 4, you get 7, and so on. Yes? So this is our series. Obviously, it is a geometric series with the ratio. Who is the ratio?
X squared.
Minus x squared. If it would be x squared, the second term would be plus x at 5. Yes, the ratio is negative x squared. Okay, and now we know the sum of this series. It can be done in 2 different ways. You can take off a common factor x at 3, and it will be 1 minus x at 4 plus x at 2, sorry, x squared plus x at 4, and so on. Yes? And now the sum of this series, it is exactly the sum of the geometric series. We ratio this one. Attention, this one here starts with 0. For the sum, it's important to start with 0. So when we are talking about the sum of the geometric series, we know that it starts with it's 1 plus q squared, and so on. This equals 1 over 1 minus q if modulo of q is strictly less than 1. So the idea is to start with 1 here. Otherwise, of course, we must subtract those terms which are missing. Yes. And now nobody's missing here inside. So it's 2. I shall show you in another way. 2x at, of course, these are very simple facts. 2x at 3 times what? 1 over 1 plus x squared. So what we did find is that the derivative of s equals 2x at 3 over 1 plus x squared. Another way to do the same is the following. Here, add and subtract the missing terms. 2 times what? 1 minus x plus x at 3 minus x at, sorry, here, no. We have x to be missing, yes, and then you have to add to subtract minus x, the one you added, and okay, the same result. So, but the simplest way to it is a common factor. So now we know the derivative of the function s. And of course, now we need to find the primitive of S. Now, a function has infinitely many primitives. So the question would be, which one of them is S of X? We shall compute all the primitives, and then we must choose the right one. Well, it's obviously from the formula of S, which is written here. Yes, for example, when you put here x, S of X here, attention here, it starts with what? It starts when we put n equals 2, you get 1 over 2 x at 4, and so on. So when you put here x equals 0, you get 0. So the function S has the property that S at 0 equals 0, and it is the primitive of the function S prime of X. So we shall choose that primitive of S prime, which vanish at 0. Okay, so let's do it. So we need to compute the primitives of 2x at 3 over 1 plus x squared. Of course, here you have a rational function, and the degree of the numerator is greater or equal than the degree of the numerator. So, of course, you take off 2 here. And here we make the division of polynomials. Every time when the degree of the numerator is greater or equal than the degree of the numerator, which we must use the division of the polynomials. So the quotient and the remainder. So the quotient is x, and the remainder is minus x. So we can write 2 integrals of x, yes, minus x over x squared plus 1. Yes. Okay, so now we can integrate very easily. Here, I shall continue here. You can follow, yes? It's 2 times the primitive of x, it's x squared over 2 minus 2 times the primitive of x over x. Actually, we shall take 2 in front. Is the primitive of 2x over x squared plus 2 is logarithm of x squared plus 1. So finally, we get x squared minus logarithm of x squared plus 1. This is the answer. So the sum of the series starting with 2 of minus 1 at 1 over n times x at 2n equals x squared minus logarithm of 1 plus x squared. Of course, modulo of x is less or equal than 1. Remember, we discovered that the series is convergent also at minus 1 and at 1. Okay, if there is any question here, we can do the same by integrating. Actually, now, generally speaking, when the series has here at the denominator here, you see, something with n, it's good to differentiate, to derivate it, to simplify this n, or the corresponding expression. If you have something like this, you multiply with some n times some power, doesn't matter. You can simplify this if you integrate somehow, yes, to simplify it. So these are the 2 operations which can be done. Okay, if there is any question here. You want another example, or you want to go further, and maybe Wednesday we shall do some. Okay, so this is the idea to compute sums of power series. Now, about elementary functions. Here you have also, we still stay in power series because elementary functions are defined through power series. Now, the most important formula here, the basic formula for power series, is the so-called binomial series, which is written here. This is the theory. We have this theory. Modulo of x is less. And from this power series, we have different, we obtain different particular important examples. Now, here you are an example of, here an exercise. Let's consider the function f of x is logarithm of 1 of x plus root of 1 plus x squared. Yes. And then, so let's consider and find the power series, which is the sum of this series, and of course the domain of convergence and so on. So this is our question. Write this function as a power series at 0. So the center is 0. Now, we have the usual technique in the lecture. The idea is to usually to look to the derivative of the function. Yes, or sometimes to the primitive, but usually it is about the derivative. So the first question here is, please compute the derivative of this function and tell me the result. Okay, what did you get?
1 over square root of x squared plus 1.
Indeed, this is the answer. So the derivative of this function is this one. And now the idea is to find the power series of this function. Here you can use the binomial series. Yes, of course, we shall take alpha to be -1 first of all. Yes, and -1 over 2, sorry. Yes, and then we shall replace x by x squared. That is simple. Okay, so now we need the power series for this function. So just take alpha equals -1 over 2 in the binomial series. So it will give us 1 over square root of 1 plus x equals 1 plus, and here we replace alpha by -1 over 2. At the end here, if you put here, if you put here instead of alpha -1 over 2, you get -1 over 2 minus n plus 1. That is 1 over 2 minus n, which means 1 minus 2n over 2, which is means because all the factors are negative, I shall put also here in front. So times the last factor will be negative 2n minus 1 over 2. Here there are dots, yes? Okay, over n factorial times x at n. Of course, the formula is valid. That's very important. If and only if modulo of x is strictly less than 1. At the end, we shall see what happens at the ends of the interval, but for the moment, that's important.
I'm sorry, it's
Yes.
not x at power 2n.
Not because I put with x, not x to n for the moment.
Oh, I understand.
Yes, yeah, I know what it's right what you say. I can put it from the very beginning, but I wanted first to obtain the formula for 1 over square root of 1 plus x. Yes.
Oh, okay.
And
Sorry.
then I shall put what I need. X at 3, x at 4, minus x at I don't know what power. Yes, as a general idea. Okay, so it's 1 plus n greater or equal than 1 of what? Let's see here what happens. So we have these are, here we have n parentheses, yes? Every one is negative, so we shall get minus 1 at n, first of all. Yes. Above we have the product of the odd natural numbers from 1 to 2n minus 1. Below we have n factorial, and from above we get 2 at n. Yes, from every parenthesis we get 2 at n. Yes. Times x at n. Okay. This is what we've got. Now, we can leave it as it is for this one, or you can here, if you want, you can change a little bit the denominator, because n factorial to at n, it means this. Instead to write this product, but it's a matter of taste. It is instead of this one, it's just take 1 factor from 2, and you get 2 times 4 times 6 and so on times 2n. So above you have the product of the first n odd numbers, and below you have the product of the first n even, above odd numbers, and below you have the even numbers, the first n odd, respectively even numbers. You can leave it as it is, or you can put it in this form. Doesn't matter. Now, yes, you are right. Now, to get 1 over root of 1 plus x squared, we shall put, instead of x, we shall put x squared. This is possible because, attention, modulo of x less than 1 is equivalent with modulo of x squared less than 1. Otherwise, we might make some changes here in the domain of convergence. But this is not the case here. So we get that this is 1 plus, the series starts from 1 here, it's minus 1 at 10, 1 times 3 times, and so on, 2n minus 1 over 2 at n times factorial, let's write like it, times x at 2n with modulo of x less than 1. So this is the power series of the derivative of our function. It can be written in this form. Okay, and now remember, we want the power series of the primitive. Yes, just take the primitive. But attention, this function vanish at 0. If we denote it by f of x, f of 0 equals 0. Yes. So finally, after we find all the primitives, we must take that primitive which vanish at 0. So please do now this operation. So integration term by term in the usual way. We did it before. Okay, so what did you get? So the primitive of 1 here is x plus, this is a constant, and here the primitive of x at 2n, which vanish at 0, is x at 2n plus 1 over 2n plus 1. With modulo of x less than 1. So this is the sum. For example, if we want to write few terms, it will give us x. Now the second term will be here with n equals 1, it will give us minus n equals 1, it's 1 over 2 times 3, x at 3, plus the third term will be for n equals 2. It will be with plus, it will be 1 times 3, and below we shall have n equals 2, yes? So it's 4 times 2 times 2n plus 1, it will be 5. X at 5, and so on. So this is the power series. You can write it now, you can include this term inside the sum, because if you put here n equals 0 and you make some, you say that 2n minus 1, it will be 1, which is not the case for n equals 0, you can include it inside, but we can leave it as it is because we don't make any convention. Okay, this is the power series for modulo of x than 1, yes? What could we answer here? What happens at the ends of the interval? What happens at x equals plus or minus 1? Well, at the ends of the interval, as you can see, the series will be, who can tell me? If we put here 1 or minus 1, the corresponding series will be what? How? Convergent or divergent? For example, for x equals 1, we get 1 plus and 1. This series is convergent, of course, because the sequence from here tends to 0. This one, yes. What you have here is bounded by 1, and times 1 over 2n plus 1 tends to 0. Is it clear that this sequence tends to 0? So we can use Leibniz test. So according to Leibniz test, the series is convergent. That means the following, that the sum of this series is actually what? It's logarithm of 1 plus square root of 2. Yes. From here, we put x equals 1. We observe that the corresponding series of numbers is convergent. So the sum is logarithm of 1 plus, put here x equals 1, 1 plus square root of 2, and so on. So there are other series of numbers which can be obtained in this way. Okay, this is about elementary functions. Another way to use the power series of elementary functions, this was an application of the binomial series, is by computing integrals, or better approximating integrals. For example, if we want to approximate, for example, integral from 0 to 1 over 4 of arctangent, I shall write in English. I wrote it in Romanian. Arctan of x over x dx. Okay, so the idea here is to replace the arctangent with its power series. So actually, the idea behind the power series is that we can use and we can work with power series as we work with polynomials. This is the actually the basic idea, because they can be differentiated and integrated exactly like the polynomials, term by term. But for this previously we need to find how to write, for example, in this case, the arctangent as a power series. And the method is, of course, we know it. I shall take it very shortly. The derivative of the arctangent is 1 over 1 plus x squared. Now, here we must recognize the geometric series with ratio minus square root of x, yes? Or if not, use the binomial function, but yes, I write this formula. Is it clear, this formula, where it comes from?
Yes.
Yes. It's the geometric series with the ratio minus x squared, yes? Of course, it holds if modulo of x is less than 1. Actually, modulo of x squared less than 1, but it's equivalent with modulo of x strictly less than 1. Okay. So now, in order to obtain the power series for the arctangent, we need to integrate term by term, but attention, and after that we need to think what primitive should we take. Well, arctangent of x equals 0, so we need to take that primitive which vanish at 0. Okay, so now we shall integrate term by term. We get this. So yes. So the formula holds if modulo of x is less than 1. So finally you obtain that the function arctangent of x is the sum of the following power series. For instance, this is not the goal of our exercise, but if you put here x equals 1, or for both x equals 1 and x equals minus 1, you get convergence series, and for x equals 1, you get the famous Leibniz formula that the sum of this series equals pi over 4. Simply because when x equals 1, the corresponding series is convergent according to Leibniz test. Okay, so let's come back to our problem. So now we have the power series of the arctangent. We shall use it to compute the integral. Yes? So it will be integral from 0 to 1 over 4 of, instead of arctangent, we write the corresponding power series. Okay, and now here we must simplify. Maybe it's useful to write few terms of this power series. When you put here n equals 0, you get x. When you put here n equals 1, you get minus 1 over 3, x at 3, and so on. So anyway, the first term is x. So we can simplify by x. Always check this. So here, instead of 2n plus 1, we shall get 2n, and here this one vanish. So it is integral from 0 to 1 over 4 of this sum. And now integration term by term. This is what I told you in the beginning. One can work with power series exactly as we work with polynomials. This is the basic idea about power series. Okay? And here the primitive is x at 2n plus 1 over 2n plus 1 between 0 and 1 over 4, which finally gives us n plus 1 squared times here, when you put x equals 1 over 4, you get below 4 at 2n plus 1. So what did we obtain until now? We obtained the following, that the integral from 0 to 1 over 4 of arctan of x over x dx equals, attention, it's not an approximative formula, it's an exact formula, equals the sum of this series. Okay, this is what we've got by using the power series associated to our tangent. And now let's express an exercise. For example, approximate the integral, this integral, with an error less than some epsilon. For example, 10 at minus 3. What should I do? Now, here we must use a result from alternating series of numbers. An alternating series of numbers, it's a series for which of the form sum of minus 1 at n times an, where an is a positive sequence. This is called an alternating series. And the basic result here, in order to approximate alternating series of numbers, is the following. If we want to approximate let's denote S the sum. We know that an is decreasing to 0. So if S is the real sum, I mean the exact sum, the error we make if we replace x by the sum from 0 to k, from 0 to n of minus 1 at k, ak minus s, this is the error we are making if we want to approximate the sum with a sum until n. This is less than an plus 1. How we said that the error is less than the first neglected term. This is the first neglected term. We add up to n, and the error we make, it's less than the first one which we neglect. That means an plus 1. So in order to apply this result, what we need to know in general is to know for which one is the least n, satisfying an less than the given epsilon. And that one will, the first n which satisfies this inequality will be the rank of the first neglected term. In our case, if we go back here, we need 1 over 2n plus 1 squared times 4 at n, in modulo it is positive, to be less than our epsilon. And from here we get n. In our case, it is 1 over 1, it is 10s minus 3. So we need the least n for which 2n plus 1 squared times 4 at n is greater than 1000. And now we make some verification here and we get n. Yes. And we shall add up to that n. For instance, when n equals 2, we get 5 at 2 is 25 times 16. This is 400, so it is less than 1000. It's not good. Let's try n equals 3. I think n equals 3 is good. Yes. So n equals 3. It's okay. So 3 will be the rank of the first neglected term. So our integral, which equals this sum, will be approximated with an error less than 10 at minus 3 by adding up to n equals 2. That means sum from n equals 0 to 2 minus 1 at 10 over 2n plus 1 squared times 4 at 2n plus 1, which gives us 1 over 4 minus 1 over here is 3, 9, 4 at 3, and plus for n equals to it's 1 over 25 times 4 at 7. N equals to 5, sorry. And now we can make the computation, and this is the value of the integral, an approximative value with an error less than 10 at minus 3. Okay, so here we end up our lesson. Wednesday, 21 hours. We can we shall meet again here to continue the preparation of the partial. But also don't forget that the main reason of the Rose lectures is to make a revision of the basic facts from the college. Okay, but it's up to you how to use these lessons. Okay, if there is any observation, suggestion, question, please. Okay,
I have a question about absolute convergence.
Oh.
So